Here we are going to study the different case of AC circuit by joining the resistance and capacitor in a series. So R plus C is present in this particular case, whereas here is the absence of inductor. And so the value of Z will now depend only on the series connection of resistance and the capacitor. So here you can see the series connection of AC circuit by using the components I and C. And as present, now I am going to discuss about the impedance of this circuit. So here Z will be dependent on R and the value of J over omega C. That is equals to R minus J into Xc, because 1 over omega C is the value of Xc. Therefore, the magnitude of Z is related to under root R square plus 1 over omega C whole square, that is equal to under root of R square plus Xc square. So this is equation number 1. Here the magnitude of Z and the value of Z are consisting of the real part as well as this imaginary part, and so the characteristic of real and imaginary axis of impedance Z is given by, so this is the relation between the real axis and this imaginary axis. Here if you want to find out the phase difference, then again you have to consider the equation of tan delta, and which is the ratio of two arms. The above arm is R, or we can say the first of all I have to consider the vertical arm, that is 1 upon omega C divided by the upper arm or the horizontal arm R. So I can directly write it is 1 upon omega C into R, whereas the 1 upon omega C is the value of Xc. So final answer is Xc over R, and with this the phase difference is delta is equal to tan inverse Xc over R, and this is the second equation for the phase difference. And remember, here the value of delta will be negative. And why it comes negative, we have seen in the case of AC circuit with only capacitor. So you can rewind that article. So here as delta is negative, so the electric current I leads the voltage V in terms of phase by the phase difference here is lambda, because we don't know the actual value of delta. Why? Because the value of Xc is not known, the value of R is still unknown, and so I can write down one general equation for current as the voltage is given by cos omega t. Here the value of delta is negative, so we have to add in terms of cosine form, and the value of mod Z is under root R square plus Xc square. So this is the third equation in this particular case. And with this, our AC circuit with R and C combination is over. Now we will switch on to the next type of combination, that is the combination of inductor and capacitor, that is L and C. Let's start the different case of AC circuit. This time we will connect the component inductor L and capacitor C in the series. So in this particular case, L plus C is present and resistance R is absent. So here also the value of impedance will only depend upon the voltage contribution on L as well as the voltage contribution on the capacitor C. So let's find out the connection. How does it look? So here is the arrangement is shown, and if we look at the value of impedance, so here Z is equals to J omega L minus J over omega C, and hence the magnitude of impedance, that means mod Z, if we want to find out, then it is under root of J square omega square L square, or in simple word you have to find out in the simple, then we can find out the magnitude as by neglecting the imaginary form, that is omega L minus 1 upon omega C. This value I can write in terms of XL in this way, JXL minus JXC, that is equal to XL minus XC, that is the magnitude of impedance. And if we look at this impedance, it has no real value. The both values are consisting of imaginary part. But here we have to assume one thing, that the value of omega L must be greater than the value of 1 upon omega C. Then the value of Z which is obtained, I am giving you such kind of characteristic in the following figure. So here the characteristics of the impedance Z in real and imaginary axis is shown. From the figure it is clear that the phase difference between real and imaginary axis is exactly pi by 2. So you can directly put in the value of current that I is equal to cos omega t plus pi by 2 or minus pi by 2. Here we have considered the greater than sign. So whenever there is greater than sign, you have to minus this angle, and suppose if there is a less than sign, then you have to add plus into this particular angle, and so whenever this delta is equal to pi by 2 and the omega L is greater than 1 upon omega C, then current is lagging behind the voltage in terms of phase by pi by 2. Now see, in your textbook it is written that what will be your characteristic or what will be your conclusion for omega L is less than 1 upon omega C. Therefore, when omega L is less than 1 upon omega C, the value of delta will be minus pi by 2, and hence at this point the current is leading the voltage by the phase pi by 2. So two kinds of effect we are getting from this particular topic, which is of inductor and capacitor are connected to each other. Now see, from which reason here we have to consider the two phase differences because of these two quantities are imaginary itself, and the above conclusion what we have made for one real number and one imaginary number, but in this present case both are of imaginary quantity. Let's start the last case in which we will consider our AC circuit with the parallel combination of L and C. And with this parallel combination, I am connecting the resistance in series. So the circuit or the arrangement will look like. So here the arrangement is shown, and if you want to find out now the impedance of this circuit, then we have to use the laws of series as well as the parallel connection. To obtain the value of impedance Z. Now see, the parallel connection means you can see from the figure that the inductor and capacitor are connected parallelly. Means the phase difference between inductor and capacitor will be 0, and here the series connection of R has been taken and the voltage is flowing from the direction of LC to R. Now let's start our analysis to find out first of all the impedance of parallel connection. So it is 1 upon Z1, that is equal to 1 upon Zc, means the impedance of capacitor and impedance of inductor. As we are aware with the the law of resistance for parallel connection, that means the resultant resistance, and here the resultant impedance is the addition of the inverse of the resistance flow of inductor as well as capacitor. And now the value of Zc is 1 over minus j upon omega c plus the value of Zl is equals to 1 over j omega L, and from both the quantities I can get common of j. So j is common. Inside the bracket omega c minus 1 over omega L. So this is actually the value of 1 over Z1, and our aim is to find out the impedance of parallel connection. So I have to invert this. Therefore Z is equal to, or Z1 is equal to 1 over j into omega c minus 1 over omega L, and as we know the value of 1 over j is equal to minus j. So minus j over omega c minus 1 over omega L. So this is actually the value of Z1. And if you want to find out the resultant impedance of the AC circuit, so that is given by capital Z, the parallel connection impedance plus the series connection impedance is R itself. So substituting the value of equation 1, so R minus j over omega c minus 1 over omega L. So this is equation number 2. Now here we are assuming that the value of omega L is greater than 1 upon omega C. Then I can represent the magnitude of Z is equal to under root of R square plus 1 over omega C minus 1 over omega L whole square. So this is the third equation. But if you use such kind of values of omega L which is greater than 1 over omega C, then the relation between the real axis and imaginary axis of impedance, that is given by this figure, and this figure suggests that the value of delta is negative, and so the value of current I can find out as Vm cos omega t plus delta. Why plus delta? Because here delta is negative and the distance which you are taking in the negative vertical side is 1 upon omega c minus 1 upon omega L, and the horizontal distance OD you are taking as R, and so the value of I will be Vm cos omega t plus delta upon under root R square plus 1 over omega c minus 1 over omega L whole square. So this is the value of current passing through it. But it is necessary that we should determine the actual value of delta in general, because at present the value of inductor and capacitor as well as the value of resistance are unknown. So it is better that we should derive a general result. So tan delta is equal to here HD and here OD, vertical distance divided by horizontal distance. So the distance HD is given by 1 over omega c minus 1 over omega L, and the value of OD is R. So I am multiplying it with the value of R, and after finding this value you just have to apply tan inverse on the right hand side, so your phase difference will be obtained. So it is tan inverse 1 over R into omega c minus 1 over omega L, which is equation number 4. And with this, our all different cases for AC circuits are over, and now we will see one important topic which gives us the value of voltage and current.